SFEE. Okay. So now let us look at the application of a SFEE. How we can apply SFEE for different devices, okay, flow devices. There are many devices to which SFEE can be applied. First one is nozzle and a diffuser. What is a nozzle and what is a diffuser? Let us see first. What is a nozzle? Can anybody answer this question? Nozzle. Have you heard the word nozzle? Yes. Yes. What is a nozzle? Have you heard the word nozzle?
Opener.
Yes, sir. Yes, sir.
Yes. Who
Yes,
is
sir.
it? Yeah. What is nozzle?
It is used to control the liquid or the gas coming out.
It is used to control.
The liquid of liquid or the gas coming out.
No, your audio is not clear. Somebody else can answer. Your audio is not clear. I cannot hear you properly. Others? Anybody else is there? Alvin, who is this? Alvin?
Yes, sir.
Huh?
Yes, sir.
Alvin, what is nozzle? You know? What is a nozzle? Anybody else?
To control
Prashant?
the
Huh?
flow of gas flowing out, to control the flow of gases.
Gas flowing out of?
So, anything you used to control it, the flow of gas.
To control, you use nozzle. You mean to say that it is a controlling device. To control the flow, it is used.
It is a opener. It is increase the speed of liquids. Yes.
It increases the speed.
It is a tube whose diameter decreases at one end. Area of cross section decreases at one end.
Okay.
There's an opening.
Okay.
Small opening.
Okay. Right. So it's a device where, as she said, a flow device with a decreasing cross section of area. So what happens when the cross section area decreases? The amount of fluid flowing, volume flow rate will not change. It has to be same. But cross section area is decreasing. So therefore, what happens? The velocity increases. Okay, the velocity of the fluid increases at the expense of pressure. When velocity increases, pressure decreases. All of you have heard about Bernoulli's theorem? Have you heard Bernoulli's theorem?
Yes, sir.
Bernoulli's theorem, three energies will remain. Sum of three energies will remains constant. Pressure energy or pressure head, velocity head, and the potential energy, that is the height, energy associated with height, potential energy. All three heads remain constant for a connected fluid, right? So when velocity increases, the pressure decreases. So like that, you can increase the velocity of a fluid. If suppose you have a high pressure fluid, you convert it into high velocity fluid. Okay. So this is used in turbines. Turbines you use nozzle. You have a high pressure steam. Steam inside boiler is stationary, right? It is not moving. It is a velocity is zero. But when it comes out of the boiler, you allow it to go through a nozzle. So when it flows through a nozzle, its velocity increases at the expense of pressure. Pressure decreases and velocity increases. So nozzle is a device used to increase the velocity or kinetic energy of the fluid. It can be gas or a liquid. For both nozzles are used. Diffuser. What is diffuser? Have you heard word diffuser?
No, sir.
What is diffuser? Yes, anybody? Have you heard word diffuser or not?
No, sir, not heard.
Okay, diffuser is the opposite of a nozzle. In the nozzle, you increase the velocity. Suppose you have a high velocity fluid, you want to convert it into a high pressure, reduce the velocity and increase the pressure. So then you use a diffuser. Okay. So in diffuser, cross section area increases along the flow direction. In a nozzle, the cross section area decreases along the flow direction. In construction, they are same. Okay. Only the way, the direction of flow decides whether the component is diffuser or nozzle. Let us see. So a nozzle is a device in which velocity or kinetic energy, Ke means kinetic energy of a fluid, increases at the expense of a pressure. Okay. So how it is? It's a nozzle. Okay. There is a pipe. Okay. There is a large diameter pipe. It's connected to a small diameter pipe here, other end, to a nozzle. Right. When when the fluid flows in this direction, the when fluid is flowing in this direction, you find that velocity cross-section area is decreasing. So when cross-section area is decreasing, velocity will increase along the flow direction. Okay, velocity. Let us say if you say v1 is the velocity at the entrance, v2 is the velocity at the exit. V2 will be more than v1. Okay, so this is called the nozzle. Right. Nozzle is used to increase the kinetic energy or to convert the pressure energy into kinetic energy. Right. So energy gets conserved. Again, energy is not created or destroyed. Right. Pressure energy is there. Kinetic energy. Pressure energy gets converted into kinetic energy. Right. One form of energy gets converted into other form of energy through a device called a nozzle. Okay. So if you see here, volume flow rate is cross section area into velocity. Volume flow rate at section 1-1, suppose at the entrance, will be cross section area into the velocity v1. Velocity at the exit a2 into v2. Since a2 is less than a1, the flow rate a1 into v1 should be equal to a2 into v2. Volume flow rate cannot be different. It has to be same. Whatever fluid is entering here, same amount is leaving here. So therefore, what happens? You must this is true for liquids, but for gases it may not be true. Okay, for liquids it is definitely. So in liquid, what happens? Whatever volume is entering must be leaving. Therefore, A1 V1 should be equal to A2 V2. So therefore, when A2 is decreases, that means V2 must increase. Okay, the product has to be same. Okay, so that is how these nozzles work. Diffuser is opposite. Suppose instead of fluid flowing in this direction, same device, if I make fluid to flow in opposite direction, right? Instead of left to right, if the fluid flows from right to left, then it is called a diffuser. That's the only difference. Okay. So in a diffuser, the velocity or a kinetic energy of the fluid decreases and the pressure energy decreases. Pressure energy increases. So see, this and this same devices, no difference. Only difference is flow direction. The direction of the flow fluid decides whether the component acts like a diffuser or a nozzle. Is it clear? This nozzle and diffuser concept is clear to you?
Yes, sir.
Yes, sir.
Yes. Nozzle and diffuser concept is clear to you? Working principle?
Yes, sir.
Yes? Okay. So now let us try to apply SFE. You can consider this nozzle or diffuser as a control volume, steady flow device, where a fluid is steadily flowing and a conversion of energy is happening. In nozzle, potential energy is converted, pressure energy is converted into kinetic energy. In diffuser, kinetic energy is converted into pressure energy. So it has an energy conversion device, okay, where flow continuously fluid is flowing. So therefore, you can apply the steady flow energy equation to the nozzle or diffuser. For both cases, you can apply. Analysis is same. Okay, let us see how we can apply the SFE to the nozzle or the diffuser. So SFE, I consider section. I call the left as a section 11, right as section 22. Okay, here section 11, section 2 for both. I am not looking at it. I am not calling inlet and exit, right? Because section 11 is an inlet for a nozzle. For a diffuser, section 11 is exit. Okay. Similarly, for a nozzle, section 22 is exit, whereas for a diffuser, section 22 is inlet. Okay. Because same equation I can make it. That's the reason I am using that. Sorry. So if you apply steady flow energy equation, we'll write the first steady flow energy equation. What is steady flow energy equation? We have seen this equation, right? It's a steady flow energy equation. Now let us try to apply the conditions. Try to find out the one after other the values. What is H1? What is H1? Anyone, please? What is H1?
Enthalpy.
Enthalpy. Enthalpy of a fluid at a section 11. What is H1? Enthalpy of fluid at section 11. What is V1? V1 bar?
Velocity.
Velocity of fluid at a section 11. Z1 is? What is Z1?
Height.
Height or elevation, right? Height or elevation from a datum reference line. Okay. What is dq by dm?
Net,
Mass flow rate, sir.
What? My God.
Mass flow.
Mass flow rate.
net rate of heat transfer.
It's a heat transfer per kg of a fluid. Okay. Net heat transfer per kg of a fluid. Okay. Clear? We can write in the previous another equation we are writing it a heat transfer per unit time. Like that also we can write. Here we are writing a heat transfer per kg of a flowing fluid. Is it clear? Is this clear? Somebody said volume flow rate, no? Who is that? Who said volume flow rate? Okay, dq by dm is net heat transfer per kg of the flowing fluid. What is H2? Yes, please. What is H2?
Enthalpy at second section.
Enthalpy of fluid at section 22, right? V2 is? What is V2?
Velocity.
Velocity of fluid at section T2, V22. This Chirag is there. Chirag, Can you hear me, Chirag? Chirag, are you there? Chirag is not there. Sudarshan Shetty. Sudarshan Shetty. Sudarshan, are you not attending class? What are you doing? Satmani is there? Satmani? Okay, these people are not attending classes. They are
Yes,
still
sir.
on. Satmani is there?
Yes, sir.
Yeah,
Yes, sir.
Satmani, what is Z2? Yes, Satmani, what is Z2? Can you hear me, Satmani? Either you say no, if you don't know, say at least I don't know. Don't keep quiet, don't waste my time here. Satmani, what is Z2? Sharat Kumar is there? Huh? Z2 is? Okay, leave it. Sharat Kumar is there? Sharat Kumar. Skanda Krishna. Skanda Krishna.
Yes.
Are you there? Can you hear me? Skanda Krishna, can you hear me? Yes or no?
Yes, sir. Yes, sir.
Now, what is Z2? Prashant is there? Prashant?
Yes, sir.
Prashant, what is Z2?
Elevation or height.
Elevation at a section 2, right?
Yes, sir.
Then G is small g, what it is? Anybody else can say this answer? Small g is? Anybody can answer what is small g?
Gravitation.
Acceleration due to gravity.
Gravity.
Then what is the last term? dwx by df.
Net rate of work.
Net rate of work.
Work transfer per kg. Okay, that is important. Per kg of a flowing fluid. That you have to say. It is not per unit time, not per second. It is per kg of a flowing fluid. Is it clear? Okay. Now let us try to simplify, apply the conditions what are existing here. So if you look at the center line, suppose if you take measurement, mean line if you take center axis, at left section 1, 1 and 2, 2 are at the same height. Yes or no? In most of the times, nozzles are small devices. The elevation difference, height difference at the entrance and exit will be negligible. Therefore, you can safely assume the height Z1 is equal to Z2. Okay, I can assume say Z1 is equal to Z2. Clear? So that means this Z1 term. If Z1 is equal to Z2, this term will get cancelled, right? Z1 is equal to Z2 equal to Z. If I write ZZ gets cancelled. Yes or no? Is it clear what I'm saying?
Yes, sir.
Hmm?
Yes, sir.
So here, so if you see this gets cancelled and this one gets because Z1 is equal to Z2. Then in a nozzle is a flow device. Fluid is flowing from left to right. There is no work done or heat transfer is negligible. So there is no heat transfer in a nozzle. So I can neglect this. This term can be eliminated because there is no heat transfer in a nozzle or diffuser in both. There is no heat transfer and there is no work transfer. These two terms can be removed. Okay. If I remove these four terms, Z1Z, Z2Z, dq by dm, dw by dm. So what I am left with? Please write down in your paper, pen and paper you have, all of you. If I eliminate four terms, what I will be left with? What equation will reduce to? Yes. What will be the reduced equation?
H1 plus V1 bar square by 2 equals H2 plus V2 bar square by 2.
Correct. Okay. So applying conditions of a nozzle or diffuser. These conditions are valid for both nozzle and the diffuser. Elevation is equal. There is no heat transfer and there is no work transfer. Therefore, we are removing them. So therefore, I will get equation. And I will simplify one more thing. In a nozzle or suppose if you take nozzle, this V1, the velocity at left compared to right. Huh? Velocity V1 will be very less compared to V2. So therefore, we can neglect the V1. It is very small compared to V2. Therefore, compared to H1 plus H2 plus V2, velocity will be very small. V1 will be very small. Therefore, we ignore this. Okay, V1 can be ignored. So if I ignore, I will get equation like this. V1 can be eliminated. You can assume it as 0. It is not 0, but it is a negligible when compared to, it's like suppose you are measuring in terms of kilometers, 2 kilometers. Then 1 centimeter becomes negligible, right? You will go to shop, you will purchase 1000 rupees, 2000 rupees, 2 rupees, 3 rupees change. You will say, okay, keep the change. Tips for you, like that. It is negligible compared to these energy quantities. Therefore, it can be neglected, right? So if I neglect the V1 velocity, you can write a V1 is very small compared to V2. Therefore, V1 can be neglected. Write down. V1 small symbol, very small symbol, very small symbol. Two small symbols you have write. Okay, clear? So then you will get equation H1 is equal to H2 plus V2 by V2 square by 2. Now write equation for V2 from this. Simplify this equation and write equation for the V2. All of you do that. Write equation for V2, velocity at section 2. Yes, what is the equation for?
Equation for velocity, sir. Velocity.
Yeah, V2.
Square root of 2 into h1 minus h2.
Yes, all of you got same answer. Everybody others?
Yes, sir.
Okay.
Yes, sir.
So V2
Yes,
is
sir.
equal to square root of 2 into h1 minus h2. So it's like that you can. Diffuser is either used to increase the velocity. So that increased velocity I want to find out. Okay. Or nozzle is used to increase the velocity. That increased velocity I want to find out. Or diffuser is used to decrease the velocity. That what is that high velocity from which it is reduced to almost when diffuser is used, the exit velocity will be zero almost. Okay. So the initial velocity I want to know. Okay. How much energy is converted into? In the diffuser we will be interested into this energy. How much energy it increased? Okay. In diffuser we will be interested in h1 minus h2. h1 minus h2 is equal to v square by 2. Okay. In nozzle we are interested in v2. Okay. For diffuser it will be h1 minus h2 that we are interested in. Increase in delta h. Okay. Delta h is equal to v square by 2. For nozzle it is velocity. Okay. Velocity is 2 square root of 2 into change in enthalpy. Is this clear? Okay. But nozzle that I showed here is a simple nozzle I showed. Normally the industrial application nozzles that are used, what happened to this? Something went wrong. Huh? Wait. Okay. So we saw equation for a nozzle, but industrial nozzles, if you see, there is something called a convergent and divergent nozzle. Okay. Initially, the normal practice for nozzles is like this. If there is a decrease in area. Okay. The velocity will increase. Then there is something called throat section, lowest diameter. Then diameter will go on increasing. So when you use such a cross section, it is observed that velocity increases here. Then after this, velocity will not increase. Sorry, velocity increases after this throat section. Logically the velocity should decrease because there's an increase in cross section. But that does not happen because there are other properties of fluids. Fluids are not ideal. Okay, in ideal fluid it should happen like this, but that does not happen. It goes on increasing. So you get a supersonic velocity is a very high velocity steam coming out of. So this is usually in steam turbines they use a convergent divergent nozzle. Okay, the name is convergent divergent nozzle. First it converges, then diverges. You get. So if there is a diverging section like this, velocity will decrease. But for initially there is a convergent section, velocity increases. Some critical velocity is achieved at the throat section. Once the velocity reaches a critical section, after that if you increase the cross section area, further velocity will not decrease. Instead velocity will go on increasing. Okay, so because the fluids are compressible, therefore what happens? This typical behavior is observed. Why it is, how it is, and all. You will study in the next semester when we discuss in detail about nozzles. There is a separate chapter on nozzles, steam nozzles. Under that, we'll discuss how it is and why it is. Now, for time being, you take it for granted. Nozzles are not something that I showed here. Okay, in the previous slide, they will not be like this. Usually, nozzle will be like this. Just for your understanding, I showed the figure like this. Okay, but usually nozzles will be. Yes, can you hear me? Hello.
Yes, sir.
Yes, sir.
There was a network issue. I got disconnected. Okay, so I was discussing about a convergent divergent nozzles. The turbines and all. Instead decreasing, it is a decreasing and then increasing. Therefore, it is called a convergent and divergent. Initially, it is a convergence, then there is a divergent. Therefore, it is known as convergent divergent nozzle. It's something that is used, and why it is, how it functions. So those details we'll discuss in the next semester when we discuss about in applied thermodynamics. There is a separate chapter on nozzles. So that time we'll be discussing how it happens and all. For time being, you take it for granted that there is something called convergent nozzle in which velocity increases, which are used to achieve very high velocities in fluids. So if you take here, but SFE is applicable for this also. Okay, section 1.1 if you take this and section 2.2 here, you can use it. Same equation you can use it. V2 is equal to 2 square root of 2h1 minus h2. Okay. Let's try to solve this problem. Please note down this problem. Okay, can you solve this problem? Try to solve this. If you cannot, please tell me. I will solve.
Sir, is it 36.6?
I don't remember. Let me see. Others? What
I've
about
used the formula V2 bar is equal to square root of 2 into H1 minus H2.
Yeah, that's fine. But there, this energy is in kilojoules.
Yeah, that kilo I've neglected. Sir, is it 1.157 kilometers per minute?
Kilometer per minute. Okay, but don't write it in kilometer per minute. You convert it into meter per second.
Because here the first initial velocity is given in meter per minute. No?
So you considered initial velocity v1. You have considered an equation
Square root of 2 into H1 minus H2.
that is neglecting. There is two parts. First part is considering the velocity. Second one is without considering velocity. Both calculation you have to do. Yes. What about others? Are you calculating? Please switch off your audio. Some disturbance is creating. Are you able to calculate? If you are not able, you tell me. Okay, I will solve that. Shant,
Hello, sir. Answer for V2, sir.
tell me.
No, not got, sir.
What is the problem?
I got
You apply-
36.60.
No. You have to use that the kilojoules. You have to substitute in convert into joules. H should be in joules.
Okay.
Sir, for first one I've got 3.78 kilometer per minute.
Per minute you got. Okay, fine.
78.
3.78 per minute. See, 1 minute. Let me check. You done like this?
Two thousand nine thirty kilo.
Hmm?
293,000, sir.
Yeah, like that you have to do.
Plus 3,600 squared by 2.
You have, I don't know whether I'll show this equation, whether you use properly that. You have used this equation?
No, I've
Yeah.
used the application of SFEE. That equation I've used.
Yeah, this here.
Yeah. Same equation.
Same equation, right?
Yeah.
So if you take the H1 minus H2, H1 minus H2 is 6070, right? If you write V2 will be equal to square root of 2 into H1 minus H2 plus V1 plus V1 square, right?
Plus
Like this. Did you get this equation? V2 is equal to 2 into H1 minus H2 plus V1 square. Are you getting this?
yes, sir.
So, what is H1 minus H2? 670, right?
Yes, sir.
670 into 2, 1340. Okay.
Sir, 670 into 2 is 7,000.
Yeah, into 1000 into 10 to the power 3. Okay. V1 is how much? Inlet velocity 3600 divided by 60. You convert it into meter per second. That's better. It's a square. So 3600. 3600 plus into bracket 2 into 6 2 into 670 into 1000 square root of this. I am getting
Sir.
1000.
Yeah, 1,430 or like 14,000 something I'm getting. Sir, but the
14.
equation over here,
Hmm.
V2, sir. Where is the 2? There are two 2's over there, right?
Okay. See.
It will become H1 minus H2
Okay. H1 minus H2. This side.
plus
You bring it.
V1 square by 2 whole that for that whole square root it will be there, right?
No. You H1 minus H2 is there, right? Plus V1 by 2. V1 square by 2. If you bring this 2 this side, this becomes 2 H1 minus H2. This 2 gets cancelled. It will remain V1. Correct?
Yes, sir. Sir, after you do the square root, you get 3.78, sir. Kilo.
3.78.
Yeah.
How is it possible?
H1 minus
70,
H2
no,
is.
sir?
How much you got?
70.
70.
Sir, H1 minus H2 is 670 kilo.
Okay.
Into 2.
Into 2. Into 1000.
Into 2 we get 1, 3, 4 and 4 zeros.
670
Into
into
2.
2. 1340. Okay. 1340.
Yeah.
So
And
into 10.
then we add it. We
No,
add
no. Here you have to multiply 10 to the power 3.
Yeah, I've taken 10 to the power 3 as 3 zeros itself.
Okay, fine.
Plus 3600 square. You get 143 and 5 zeros. You get 143 into 10 to the power of 5. The square root of that will be 3.78 kilo.
Sir, I got 1.15 kilo.
Yes, how much you got answer? Yes. Prerna, did you solve that?
Yes, sir.
How much you got?
Sir, after calculating what are there under the square root, I've got 143 into 10 to the power of 5.
143 10 to the power 5.
Yes,
No.
sir.
How it is possible? See,
Sir, 1.15 kilojoules.
1
Kilos.
point, 1.15 kilometers per second you can get. That
Yes, sir.
1.15 is correct. 1.15 kilometers, right? Who got that value?
Prashant.
Prashant. Prerna, check your answer once again.
Okay, sir.
Simple it is, simple calculation. Try to do it once again. This V should be in meters per second only, not meters per minute, okay? Because only when it is meters per second, you get it in joules. This value will be in joules. Otherwise, it will not be joules, okay? Please don't take it in minutes. You have to take it in meters per second. Others are able to calculate. Are you getting same value? What about others? Alvin, did you calculate? Alvin? Rakesh? Rakesh?
Sir. Yes, sir.
What value you got?
5 meters per second, sir.
1.15 meters per second, kilometers per second, right?
No.
Okay. So now calculate, neglect this. Remove this V1. Just calculate a square root of 2 into H1 minus H2. What value you will get?
ತೊಟ್ಟದುಂಟ
1.157, sir.
1.157.
157.
Not much difference, right?
No.
1.159. Here it is 1.157. So that is the reason we neglect. Okay, because it will not much make difference whether you use this V1 while calculating or not. The final value will not be much difference. Okay.
Yes, sir.
That is the reason we neglect the V1. Okay. If you use V1 and calculate, it's okay. If you don't use it also, it's okay. If somebody in equation he has given V1 means that is meaning you should use it. Okay. In the question problem, in the numericals that is given in the question paper, if he mentions inlet velocity, then you have to use this equation only. Okay. Don't neglect them. If he does not give, then you can neglect. Okay. Clear? Is it clear to you?
Yes, sir.
Okay. I think we'll close session here today. Next class we'll discuss. Shall we have test on Friday? Test on module 2. Module 2 test. Test or which one you like? Quiz or test?
Sir, try quiz, sir.
Quiz,
Okay, sir, quiz.
Yes, sir.
okay. I'll schedule quiz. You online quiz is there. You attended quiz in other subjects, right? Already.
Yes.
Yes. I'll schedule a quiz and let you know you attend that. Okay, fine.
Okay, sir.
Shall we stop now?
Yes, sir.
Okay.
Sir.